Lab Guy here. Today I want to talk about the utilitarian nature of color bars as they apply to color television. This discussion will be format independent. It doesn't matter if we're talking about NTSC, PAL, HD, SD, mechanical TV. I want to speak generally about the color bar signal, how it is created, and how it is used. This will be a simplistic overview of the subject. I will be using the mathematical coefficients that were developed in the 1930s and 1940s in early color television. High definition color television today uses a different set of weighting coefficients for the red, green, and blue signals, but the principle of the generation of that signal is still the same. So we're not going to worry about absolute numbers in that respect. Why am I producing this video in the middle of my NBTV series? My current project, the 10-4 Eleanor, is a video signal generator. It uses red, green, and blue generated frame information from 3 separate memory chips that come out of 3 D to A converters as red, green, and blue video. In addition to that set of signals, the Eleanor also outputs monochrome composite video, let's call it. That is a monochrome video signal. A monochrome means black and white, with sync pulses added. The RGB outputs do not have sync pulses. The monochrome signal is the source of sync in that regard. So in order to generate the black and white signal, as I do in the 10-4 Eleanor, and for your understanding of it, if you're not well versed in television video signals to begin with, this video will delve into the creation of the black and white portion of the signal. I will touch on the color components of the color bar signal for completeness, but this is not a deep dive into color bars. This is a general overview. So let's begin. We've all seen the color bar signal that you're looking at right now. As you can see, it is composed of 8 vertical bars. This is a high definition image that I created in Paint Shop. The sequence of bars goes from white, yellow, cyan, green, magenta, red, blue, and black. So we've all seen these all over the place, and probably didn't appreciate how much is going on there. So the first thing that will be very helpful is let's look at the individual red, green, and blue frames, but not in that order, because that's not necessarily the order they're produced in, although it's arbitrary. So let's look at the green frame. In the green frame, half of the frame is white and half of the frame is black. Let's look at the red frame. In the red frame, we have 25% white, 25% black, 25% white again, and 25% black. Let's look at the blue frame. The blue frame is 4 stripes of white, making up 1/8 of the width of the frame each, and 4 stripes of black in an alternating fashion. The astute observer will note that looking at the green again, we have a 2. Looking at the red, we have a 4. And looking at the blue, we have an 8. That's 2, 4, and 8, which is a binary count. Let's look at the waveforms that those images represented. You'll note on the left side that the output names are the outputs from a binary counter. QC0, QB0, and QA0 represent the outputs of a binary digital counter. For some reason, the industry generates the count in reverse, which is just arbitrary. We could mix these signals around. You could put the green square wave for the red, and you'll still get the same 8 bars, the difference being the order they appear in. You'll note across the top I have labeled 8 positions called the count. They count backwards from 7 through 0, and each count represents one of the bars. Looking at the count 7, that is the binary number 7, you'll note that the 3 bits are 1, 1, and 1. They're all on. They've been scaled to fit a voltage range of 0 to 1 volt. And in that first bar position, number 7, you'll see that red, green, and blue are on. And if you know your tri-stimulus colors of red, green, and blue additive primaries, you paint mixers out there, don't argue with me. Paint mixing is subtractive secondaries. We're not covering that today. We're talking about adding 3 light sources of red, green, and blue together in the proper proportions to fool the human eye into believing it's looking at white light. So when those 3 signals are on, we get the white bar. Let's take one step to the right to position 6, and you'll note that the green signal is still on and the red signal is on. The blue signal has turned off. It's 0 volts, and that produces a yellow bar. Red plus blue in additive primary gives us a yellow bar. Let's take one more step to the right and look at position 5. You'll note that the green signal's on, the red signal is now off, and the blue signal is on. So that's blue plus green, and that gives us a color we call cyan, or blue-green. Moving right one more step to position 4, you'll note that the green is still on, the red is still off, and the blue is now off, leaving us with just green. That's our green bar. Moving to position 3, you'll notice now that the green signal has turned off, the red signal has turned on again, and the blue signal is on, and blue plus red in additive primaries produces magenta. Some people call it purple, and that is the blue-red signal. Magenta is a color that does not exist in the spectrum. Moving one more step to the right, looking at location 2, you'll note that green is off, red is on, and blue is off, so we only have red, and we have a red bar. Moving to position 1, green is off, red is off, and blue is on, giving us the blue bar. And in the last position, all 3 signals, green, red, and blue, are off, giving us the black bar. Those are the voltage waveforms from a red, green, and blue generator as they would appear on the red, green, and blue output jacks of a generator. This signal is simplified. It has no synchronizing signal. Looking at an expanded view of our red, green, and blue signals, you'll notice that below the red, green, and blue, I've calculated the waveforms for the Y signal, which is luminance, or black and white, in a video system. Whether it's color or a black and white system, there's a black and white signal. A color difference signal called R minus Y, and a color difference signal called B minus Y. R minus Y is the symbol for the red signal minus the luminance signal. And B minus Y is the blue signal minus the luminance signal. Now, why would we do that? The reason for that is that in red, green, and blue, when you're talking about the luminance, the black and white portion, that is the portion of the signal that is redundant in all three of the red, green, and blue signals. So why would we transmit redundant information? The answer is you don't. So first, you derive the black and white equivalent signal. This was done in the late 1940s, early 1950s in order to create a compatible color television signal, meaning that it was compatible with black and white televisions, because to introduce color television to the viewing public, you didn't want everyone to throw away millions of black and white televisions that were already in existence. You didn't want those millions of black and white televisions to be incapable of displaying the color broadcasts. And you needed a system that would allow a color television to display black and white broadcasts, because at the time of the introduction of color TV, black and white was dominant. Color programming was rare. So RCA and a think tank called the Hazeltine Group did the preliminary theoretical work to create this signal system that allowed black and white televisions to show a color program in black and white, and a color television to show a black and white program in black and white, and of course a color TV to show a color picture in color. So the first thing that they did was derive Y, the signal called Y. This is an arbitrary symbol assigned to the black and white component of the signal. It represents the brightness information. And Y is made up of proportions of red, green, and blue added together. Looking at the right side of the Y signal, you see my equation that says Y equals 0.3 red plus 0.59 green plus 0.11 blue. That big word I used in the beginning of this video, coefficients, just means a multiplying factor. Or in this case, we're actually dividing. And in the deep dive of the 10-4 Eleanor, I will explain about multiplying and dividing voltages by mathematical coefficients or multiplying factors. So we need 30% of red added to 59% of green added to 11% of blue. If you take those three coefficient numbers and add them together, they add up to 1. Okay? This is a normal coefficient matrix. They usually add up to 1, or whatever the scale of the matrix happens to be, but that's outside the range of this discussion. So you now see how the Y signal is made, and if you look at the waveform, you'll note that when we have a white bar, the value of the gray scale is 1.00. And In this case, I've scaled the signal so that it goes from 0 volts, the scale is on the left side, it goes from 0 volts to plus 1 volt. So if it's 0 volts, it's black, and if it's 1 volt, it's peak white, and then the other 6 levels in between represent gray levels. You'll note that the yellow is the brightest of the primary colors, and it has a brightness value of 0.89, and that is what you get when you add 0.3 and 0.59 together. The red and the green are added together there, and that's 0.89, or it's 1 minus the 0.11. Moving to the cyan bar, you'll see that it has a brightness value of 0.7 because we are taking the 0.59 of the green and the 0.11 of the blue and adding it together, and you get 0.7. Now, another characteristic of a 3-position matrix, if you take any 2 of the coefficients and add them together, you end up with a value that is the same if you took the remaining value and subtracted it from 1. So, anyways, moving on, you'll note that the steps go right down the line in proportion to the brightness of the primary color. Green has a primary brightness of 0.59, a luminance value of 0.59, excuse me. The magenta has a luminance value of 0.41, red is 0.3, as indicated in the equation, blue is 0.11, and of course black is 0. Black represents the absence of light. So that is how the luminance signal is derived, and that is what is transmitted for television broadcasts for the black and white television receiver to receive. Now, if we take the red signal and subtract that Y signal from it, you can see in the next waveform down what the result looks like. You get the difference signal. And the reason we can transmit a difference signal is because at the receiving end, we take R minus Y, which is carried on a separate carrier, and we pull it out, and we add Y back to it. And guess what we get? The equation would be R minus Y plus Y. So the minus Y and the plus Y cancel out, and we're left with the red signal again. We get our red signal back. The same applies to the B minus Y waveform on the bottom. We take it at the receiver, we separate it. We say B minus Y plus Y, and we get our blue signal back. And if we then do some more magic with the matrix, we can get the G minus Y signal, which they don't transmit as it's unnecessary. In this system, as long as you have any of the 3, there's actually 4 signals, G minus Y is not shown because in the system G minus Y was never used. Now, in television receivers, if you look at an old schematic, you will see the G minus Y signal is derived just before the cathodes or grids of the tricolor picture tube. But that's an obsolete system and is no longer in use. But that is how you would get all 3 of your red, green, and blue signal back. So that's the basis of generating the preliminary color signals for transmission of a compatible color TV system. If we were in a closed circuit world where we could have 3 coaxes running to every house and guarantee that they are exactly the same length to within a fraction of a millimeter so that the delays are constant, we could send red, green, and blue signals to anybody who wanted to receive them, and the pictures would look awesome. But we don't live in that world. We need to send those three signals through a single channel, and this was the answer to that problem. Now, using color bars and an oscilloscope, you look at the waveforms that I've drawn out here, and you can see them on the oscilloscope, and that's what we're looking at now. We're looking at the Y, R minus Y, and B minus Y signals, or actually the B minus Y and R minus Y. I've got my scope probes backwards. And they look just like the drawing that I showed you. And then in the next scope shot, you see them as red, green, and blue waveforms. Again, derived in the real world. So that is the process of red, green, and blue being converted to Y, R minus Y, and B minus Y color difference signals. And in the 10-4 Eleanor deep dive, you will see the Y equation played out in resistor values. Very simply, don't panic. Nothing to panic about. And in fact, you will laugh when you see how easy it was to get those resistor values. So I hope you found this introduction to color bars interesting and informative, surprising and enlightening. So until next time, this is Lab Guy saying, Lab Guy out.